center of the center of mass and in the center of mass. And what a grand and wonderful simplification that is. And what is it that allows us to make that miracle? And the answer, so he talks about T and then later U, the kinetic and potential energies. But you see in the case of the kinetic energies that there's the assumptions in that are not very huge. That essentially it's just Galilean relativity, and once you're there, then you can certainly break up the kinetic energy into the kinetic energy of the center of mass and within the center of mass. And you can certainly take the two-body problem and break it down to be an effective one-body problem about the center of mass. And you didn't have to make many assumptions to do that, but the same ones that we've been making to get to the Lagrangian. And so at that point, we haven't said anything about forces. Nothing about central forces. And once we introduce central forces, then you get a whole bunch of other things that are true. But just to wake you up a little bit, let me talk about an example that I came across just a couple of years ago when we started thinking about geoneutrinos. So one of the things that we have done in my research business is we have detected the neutrinos from all of the radioactive decays in the Earth. So there's material in various layers around the Earth. And the Earth, to first order, we can treat it as symmetrical. So I want to ask you guys, suppose I tell you these are symmetric layers, and I'm sitting up here, and I want to calculate the neutrino flux at my detector here. And I know the decay rate per unit volume. What's the easy way to go about that?
Gauss's law, basically, except for neutrino flux.
Good, he took the bait. That's wrong.
It's the easy way.
Right, and so that's why I bring up this point, is because everybody, including me, your first answer is going to be likely, oh, I'll just take the equivalent of the center of the Earth, and then I'll do 1 over r squared from the center of the Earth, calculate the flux. But it's wrong.
It's not uniform. Would the neutrino decay rate be uniform throughout the entire volume of the Earth? Because
Well,
you don't have one
either
chunk
way,
of substance.
I can take it in successive spheres throughout the Earth, but it's wrong. We're so used to thinking about things like for Mr. Gravity, in fact, it's right. And the reason is that gravity is a vector force, and we're adding up, in this case, summing up the contributions from all of these guys. And it's not so simple. You got to do the damn integral over here, and they add up like 1 over r squared to each little point. And it turns out that it is not equivalent to replacing it. The reason that it works for Gauss's law, which thank you for getting suckered in on, is that for every little piece over here, there's another piece over here, so that the transverse parts of the vector cancel out. So I get to add the whole thing up. But I thought that's a nice example to bring up for you, where the simple idea of replacing by the center of the mass does not work. And we're so used to these lovely cases for electrostatics and for Mr. Gravity, where we can get away with that kind of thing. But just to set the stage that this is not always the case. Now it'll be the case, as we were talking about, for the kinetic energy, when we're adding up for a system, that'll be all fine. But when you start talking about the potential energy, or the central forces, then it's going to be okay for central force. But then adding up the neutrino flux is not a central force, even though it falls off like 1 over r squared because of conservation of energy and so on. Okay? Just so you don't get too lulled into accepting that. Okay, so then he goes through the usual, the same ritual that we talked about from Landau earlier, and conservation of the equations of motion in the first integrals, and you get conservation of angular momentum and linear momentum, and you get out Kepler's laws pretty quickly. The aerial velocity is a constant. All of that's pretty straightforward, and he just goes through all of that. And so then he goes through here several different ways of writing up the discussing the equations of motion in a simple central force situation. And of course, the classic the classic one is when you start to write down you just invert the equations of 1/2 m r dot squared plus 1/2 L squared over m r squared plus v is equal to a constant. And invert that into then an equation for t is equal to the integral from sum r0 to r of dr over square root of 2m 2 over m e minus v minus L squared over m r squared. So in all of these games you can go about, depending on how you want to handle the angular momentum term, putting it in as a rotational energy, or putting it in as a pseudo force, or whatever. It's convenient to handle it one way or the other. And then once you have that, then you can just immediately make a change of variables and wind up writing it as. So you have the integral over time to get the equation of motion, r squared of t plus some initial theta naught. So in principle, now we're all done. We're finished. This is it. We've solved all the orbital problems, right? There it is. It's trivial.
Evaluate it.
Yeah. Just do the integral, okay? Don't give me a hard time. Just do the integral. But of course, that is just the problem, that most of the time that integral is an awful monster. And so, indeed, you can say that you've solved all the problems. That's a theorist's solution. Now it's just a matter of an exercise for the student to carry that out.
Can I ask a quick question?
Yeah.
In 316, how come they dropped the plus and minus? You know, when you square root both sides, that kind of deal?
What, in equation 316?
It's right before
Oh.
you introduced that thing.
Yeah, that's a good question.
Looks like it's the magnitude of our.
No, that's just saying the velocity.
Well, yeah, but okay, I
That's not the
suspect that
velocity.
it's a choice to have the velocity be positive. I suspect everything will run
So vectors,
just fine backwards.
you bold vectors.
Time
so
reversal.
I don't think that's a vector that he's trying to represent there.
Oh, he's just talking about magnitude R?
Yeah, but could R be negative?
Well, our
You mean, could this
R
be
dot.
slowing down?
Or R would be negative, or dot, I guess.
Yeah, R can never be negative because it's just the magnitude. but
R can't,
You
but
can
R
have the
dot
thing
can
slowing
certainly
down.
be.
Yeah, but the magnitude is still.
yeah, the magnitude can't be.
I think, yeah. I'm-
Magnitude
I
of
don't think he's
anything is
talking about
positive.
R dot vector.
Yeah, that's right.
So yeah, there's some sneaky little conventions slipping in there.
Because because your Lagrangian is a scalar quantity, right?
Mm-hmm.
So you wouldn't want to have a vector in your scalar quantity, so R dot here is just a scalar.
Okay.
Because that's the R dot relevant to the Lagrangian of the system.
Okay, so then he goes through a bunch of falderall about, not falderall, but
What's that word?
falderall.
Okay.
What's that?
Don't ask me how to spell that. Probably of Shakespearean origin. Writing the equation of motion in terms of a one-dimensional quantity is a function of r, which indeed is something, again, with the two-body problem that you can do. And so you can then wind up writing the whole thing as just motion in r. If you ignore the angular motion, and of course it'll look like some periodic function in r, and you can write down the solutions that way. And that has some usage, and you were saying you got confused by the graphs here, that when we get up to around page 79, the 3.3, 3.4, 3.5.
That's probably more of a case that I was studying this at 1 in the morning while my baby was crying.
That's usually when, right here. But this is very useful to have a description of this in these terms, and it's something you will see time and again when we're talking, especially in quantum mechanics and so on, about orbits and bound orbits and so on. So when you have a potential, when we have a potential with a dip in it, so whichever case we're looking at, if you have a potential, this is some distance, and this is some v of r, and it may include the centrifugal force term, so that you can get an equation which goes like this, and however we want to put it. If you're the neat thing about writing it this way is you immediately can say a bunch of things, like if I know that my total energy in the system, then I know that these are the turning points, that I can calculate these points here, and I know that my orbit will be between those 2 points, and that I also know that the point which will have a fixed orbit will be down here, so I could take the second derivative of this function, right, and solve for the zero curvature turning point and find this point. So this is the point that will lead to a circular orbit.
No turning points.
And no, the 2 turning points move together as I move down here. And then, of course, when I'm up here, it's off to infinity. There's no bound on the upper end. And so in various forms, you'll see some potential like this for the discussion of atomic orbits and everything else, and or attraction between atoms, van der Waals forces and so on, or even in QCD, although people don't usually talk about the QCD forces at the subnuclear level in these terms, but something's going on to keep the quarks from collapsing to a point. There's got to be some repulsive core and then some attractive region to keep them in place, and in the nucleus, amongst the nucleons, same sort of thing. Must be a hell of a big attractive force in the nucleus to keep the positive repulsive potential from throwing the protons out, right? So there's that big attraction, but yet the nucleons don't all fall in on each other. So you'll always have some sort of a situation like this for contained orbits. So then you can have lots of discussion about what kinds of orbits. And this is kind of fun, the discussion of in what kinds of systems do you have stable orbits? Not only 1 over r squared, but if it's some other form, 1 over r cubed, whatever. And what you find in general is that a lot of these other situations you don't get closed orbits, and you may not even have any stable orbits at all in some circumstances. 1 over r squared is a super special system, and that's certainly one of the big mysteries of physics, right? Is that 1 over r squared, and this is what set Mr. Einstein to thinking 100 years ago, that looks like geometry. If you have a force law that falls off like 1 over r squared, that's falling off just like the area, which is 4 pi r squared, right? So you can think of it in terms of lines of force, that there's a conservation of lines of force, and the density of the lines of force tells you the strength of the field. So it's very suspicious that this magic 1 over r squared seems to occur in 2 extremely fundamental cases in our universe, and 2 of the most important, Mr. Gravity and in terms of electricity. So what's going on with that? And that puts you to thinking that maybe 1 over r squared has got to do with, fundamentally, with the geometry of space, and that then led to the thinking about general relativity and so on. Jumping ahead a little bit, the irony of this is that once general relativity was formulated and the mathematics cranked up for it, what we find is that general relativity itself spoils the 1 over r squared. And that rather than having orbits in space as, say, even the planetary orbits like Mercury, which is going the fastest, that the orbits, instead of having a fixed ellipse, aside from some things like coupling of the angular momenta and so on through not asymmetric bodies, but that the general relativity itself leads to a precession of the perihelion. That's to say, the ellipse is walking around a little bit, as indeed apparently it does effectively in atomic systems. And that then leads to this description of frame dragging in general relativity. So general relativity winds up that one way to treat it is that your frame is rotating a little bit. So as usual in physics, once we start digging in great detail, then you find some of these simple things get a little more complicated. But 1 over r squared is extremely special, as I think you already know from discussion of, for instance, for the Coulomb force, the fact of 1 over r squared falling off the way it does for both charges, and the equality, the exact equality, another strange miraculous thing, the exact equality of the charge on the electron and the proton being opposite and equal, which is especially peculiar given that the proton, we know for sure, is made up of 3 quarks and some other ephemeral quarks coming and going, the so-called sea or ocean quarks, that the charge doesn't have some little adjustment to it. But charge conservation is one of those things that seems to be one of the few really inescapable laws in this universe. And we know that very well because of the sensitivity of the tests of neutrality of objects like this. That there is no net charge on this object or larger objects, just due to the fact that E minus and P plus are not exactly equal, and there's some little correction in there. You know, so we talk about all these other things where there are a lot of little corrections for angular momentum and the energy state and the hydrogen atom and all of this stuff. But there ain't no correction for the total charge, as far as we know, and the limits, the experimental limits, because of the 1/r² law, are exceedingly strong. And they just cancel each other out. One of those things to sit and drink a beer and think about. How come? So there are these several very, very magic things. And the 1/r² force law is one of those things that just got to make you scratch your head about. Right. So you can read through all of this and you'll see your old friends in different clothing sometimes, like the simple harmonic oscillator always pops its head up. And then, okay, then he goes through the virial theorem, which we already did a la Landau, and pretty much the same kind of a formulation, that the time average of the kinetic energy of the ensemble is minus a half the time average of F dot R for the ensemble, in the more general way of writing it. And so, who was saying that you were encountering this in StatMech?
Well, we were using Landau. I don't think we've seen the virial theorem.
Oh, okay. But somebody mentioned that the formulation was what had come up in your StatMech class, and I had forgotten about this application to talk about how to derive PV equals nRT.
We did that.
Ah, you brought that up.
Oh,
Chester? In
Yeah,
Chester's
yeah,
class, okay.
Ryan's in the class too. We did do all of that, just kind of a...
Right. I mean, as you know very well, you can get that out of more simple but less rigorous derivations, just talking about balls bouncing off the wall and so on. Shut up. And so anyway, yeah, that's kind of nice. But then of course, also as we had seen in the Landau formulation, you can write it as the average of the kinetic energy term is equal to the average of the potential energy term times n+1, where the force law goes as r to the n. Just in case you run into a universe in which it's not 1/r². I don't know if you guys fully appreciate the usefulness of this virial theorem, but indeed of this whole formulation, my good friend Brent Tully up at IFA is one of those people that use it all the time. The astronomers. This is how we learned about dark matter. Was the application of the of the virial theorem. And how this works is that people